Listen, in crystals, there is an important law called law of constancy. Law of constancy of interfacial angle. Law of
Sir,
constancy of interfacial angle. Carefully. Law of constancy of interfacial angle. What? Listen, suppose you take a particular crystal. For a particular crystal, observe carefully. For a particular crystal, right? The angle between faces. Listen, you know very well. Suppose let us assume that I'll take a cube. I'll show you what is meant by face. I'll take a cube. Right. I'll take a cube. Listen here. See this side. This is one face. Similarly, this bottom is another face. Right? Like this cube totally has 6 faces. Now, the angle between this bottom face and this face, this angle, the angle between these two faces, right? It is actually a constant, right, for a particular crystal, right? If the two faces are, listen, if you see, the crystal may be of any shape, right? When you prepare crystal, right, the crystals appear in different size and different shape, whatever it is. But inside the crystal, the faces, right? Suppose if these two, I'll take two faces, right? And this face has a specific notation, and this face may have a specific notation, right? For the same two faces, okay, I'll take one space, say, let me call this as A and this face as B. The angle between these two faces, right, is a constant. Now, in the same crystal, you take in some other place, you take the same faces A and B and measure the angle, you will get the same angle. Okay, so what this law is that for a particular crystal, right, if you take two particular faces, right, the angle between the two faces, right, must be a constant. Okay, for a particular crystal, right, this angle is a constant, and this is what we call as law of constancy of interfacial angle. Okay, take note. Next one, law of constancy of law of constancy of symmetry. Listen, you take a crystal. That crystals may appear with a different shape. Okay, the crystal may appear with a different shape. Whatever maybe it is, right? The unit cells present in the crystals are one and the same. See, what I'm trying to say is that, suppose I'll take a crystal, say copper. Copper metal exists in the form of a crystal. Suppose I'll take a copper in this shape and another copper in this shape. By appearance, they exist in different shapes. But if you observe the crystal structure or the unit cells, the unit cell present here and the unit cell present in this copper, they are one and the same. Okay, observe carefully. Let me give this point. Listen, for a particular crystal, whether you take copper or sodium metal, whatever it is, for a particular crystal, okay, the number of symmetry elements is a fixed number for a particular, because listen, whether normally we look for symmetry not for the entire crystal, we observe symmetry for a unit cell. So you take the crystal, and for the crystal you take the unit cell, or you identify the unit cell. For the unit cell, you try to identify what are all the symmetry elements possible. Okay, for a particular crystal, number of symmetry elements, total number of symmetry elements is a constant. This is very important. Okay, suppose if you take a body centered cubic unit cell, for body centered cubic unit cell, the symmetry elements is a fixed value. Similarly, if you take hexagonal unit cell, it has a definite number of symmetry elements. So for a particular crystal, number of symmetry element is a constant. This is what we call as law of constancy of symmetry. Okay, this is applicable only for crystals, not for amorphous substance. Okay, take down. So the next important.
Sir, once repeat பண்ணுங்க sir.
Now listen. What is mean by face, edge and vertex of a unit cell or of a crystal? What is the meaning? See, for this purpose I took a cube and I have shaded two faces here, the bottom face and the left side face, this face. Okay, so each surfaces which form the unit cell, each surface which form the unit cell is called a face. So a cube has 6 faces. Listen, I just shaded only 2 here. Okay, actually a cube has 6 faces, you know very well. Now what is meant by edge? The line where 2 edges meets. Listen, just observe my hand. So this is, assume that this is one face, this is another face. Now the 2 faces joining at a particular line. Okay, here see the line which actually joins the 2 faces is what we called as an edge. So here see, I have drawn a line here. See this line which connects this face and this face. Okay, so the line connecting 2 faces of a crystal is called an edge. Okay, then what is meant by vertex? Vertex is nothing but corners. Okay, but in crystal we won't say it is corner, it is actually the meeting point of 2, 3 or more faces. It is actually the meeting point of, see here, this face, this side face and top face. These 3 faces are meeting here, joining here, correct? So the meeting point of 3 or more faces, 3 or more, not 2, 3 or more faces is called a vertex. We simply call this as a corner. Okay, we often for our convenience we call this as a corner. Yes, corner is a vertex. But what is the definition of a vertex? The actual definition is it is the point of contact of 3 or more faces. Point of contact of 3 or more faces is called a vertex. Okay, actually these 3 are related by an equation. The equation is this: number of faces is equal to number of edges minus number of vertices plus 2. Take down. These 3 are related by this equation. Number of faces is equal to number of edges minus vertices plus 2. Okay, now let me use I'll take different unit cells and I'll show you how to find, okay, the number of faces and number of edges, or how many faces, how many edges are actually exist for different types of crystals. Okay, we'll discuss, or for different types of unit cells. Right, now let's start with the tetrahedron. Just follow this carefully. It's very simple concept, but we expect questions right, in the competitive examinations, right, from this particular area. Number 1, first I'll take unit cell. and here I'll write number of faces F, number of edges E, number of vertices V. Okay. Now first I'll take a tetrahedron. Tetrahedron. You know very well how a tetrahedron look like. See, let me just draw and show you. Just draw a triangle and you take a point at the top and connect this point with these corners. This is actually a tetrahedron. Now in tetrahedron there are 4 faces, right? Here one face, this is 2, and back side we have 3 and bottom we have 4. So 3, 4. Observe carefully. I am just showing here a 2-dimensional picture, but tetrahedron is 3-dimensional. Okay. Let me write here. Yes. So tetrahedron has 4 faces. Okay, good. 4 faces. How many edges are there? How many edges? See, this each line represent an edge. 1, 2, 3, 4, 5, 6. Am I right? Just check it. Listen. A tetrahedron has 4 vertices. Okay. You can also check it with the formula. F is equal to E minus V plus 2. See whether this formula obeyed or not. Number of faces 4, number of edges 6, number of vertices 4 plus 2. Just check it. The second unit cell that I have taken here is cube. You know very well a cube. Let me draw here. Suppose if you are not able to identify number of faces, okay, if you are not able to identify number of faces, what we can do, you identify edges and vertices, then use the formula and find out face. Okay, so face, edge, vertices. Now for this particular cube, see this cube, tell me how many edges are there. So a cube has 12 edges. Now how many corners are there? See, a cube has 8 vertices. Now tell me how many faces are there. The next example here, I have taken octahedron. For octahedron, you tell me how many edges, vertices. There are 6 vertices. Then tell me how many faces are there. Number of faces, edges minus vertices plus 2. So you will get the answer as 8, which means, listen, there are 8 faces. That's why this shape is called octa. Octa means 8. So octahedron. Okay, take down.
12, sir.
So the next shape is dodecahedron. Dodecahedron has 30 edges and 20 vertices. Therefore, there are 12 faces. Okay, that's the reason why it is called dodeca. Dodeca means 12. Okay, take. So for icosahedron, there are 30 edges and 12 vertices. So you try to find the icosahedron has 20 faces. Okay, take two. First, let me find out axes, right? How many axes of symmetry are available for a cubic crystal? Okay, right? I am going to find out axes. Axis of symmetry. Axis of symmetry. Observe carefully. So I'll take a cubic shape or cubic unit cell. Cubic crystals have cubic unit cell. Okay, cubic crystals have cubic unit cell. So I'll take a cube. Now we need to fix some imaginary axis. If I rotate along that axis, we should get an equivalent shape. Okay, so what I'm going to do, listen. Now I'll fix an axis passing through the center of the top face and the center of the bottom face. Observe carefully. Now I'll fix an axis here. This axis passing through the center of the top face and center of the bottom face. That is centers of the two opposite faces. If I rotate by 90 degree, I'll get equivalent shape. Can anyone tell me what is the order of this axis? So here this axis is a C4 axis, right? 360 by 90 will give 4. So it is a C4 axis. Now you tell me, like this, how many C4 axes are available in this molecule or in this. Listen, so this is actually a C4 axis, right, which is passing through the centers of the opposite faces. Similarly, you can keep two more C4 axes passing through the opposite faces. Okay, so from the picture it is very clear. So you take this center and this center and fix an axis. This is a C4 axis. Similarly, the front face, center of the front face and center of the back side face, you fix another axis here, another axis. Okay, this is also a C4 axis. So in a cube, okay, or for a cube, there are three, let me write here, there are three C4 axes exist. Each axis is called a symmetry element. So how many C4 axes? There are three C4 axes available in cube. Okay, take note. Now, apart from C4 axis, okay, a cube also has C3 axis. How? See, you take this corner and diagonally opposite corner. See, carefully, you take a corner and diagonally opposite corner and you fix an axis, imaginary axis, passing through this. Okay, now see, listen, this is actually look like see, if you view from the top side, okay, from this corner, if you view, it look like an equilateral triangle. So if I rotate by 120 degree, okay, see, this will come here, this line will come here, or edge, this edge will come here, this edge will go here, and this edge will go here. Okay, if I rotate by 120 degree, okay, through this corner. So 360 by 120 is 3, therefore this axis is called a C3 axis. Okay, is this clear?
Sir, every 4.
Listen, so each C3 axis passing through diagonally opposite corners. Okay, so in a cube there are 8 corners, therefore there are 4 C3 axes possible. Okay, there are 4 C3 axes possible or exist. Okay, take note. Apart from C4 axis and C3 axis, a cube has also got, okay, C2 axis. So I am going to show you, right, how to fix C2 axis and how to find number of C2 axis that is possible in a unit cell. Yes, how to do that? Listen carefully. See what I am going to do. I will take two opposite edges. So suppose I will take this edge, then this edge, opposite edge. Now take the center of this edge and take the center of this edge and fix an axis passing through that. Take the centers of the two opposite edges. If I rotate by 180 degree, what will happen? This bottom will go up and top will come down. You will get equivalent shape. And 360 by 180 will give 2. So this is a C2 axis. Okay. So each C2 axis passing through the centers of the opposite edges. Okay. In a cube, there are 12 edges available. Therefore, there are 6 C2 axes possible. So there are 6 C2 axes exist in a cubic unit cell. Okay, these are all the axes possible. What are the axes? 3 C4 axes plus 4 C3 axes plus 6 C2 axes. So totally 13 axes of symmetry. Okay, axes. Now, apart from axes, a cube also has got planes of symmetry. What are the planes of symmetry? We'll discuss. Take note. Observe carefully. Let me take a cube. Here. Drawing cube is very simple. Okay, you take a cube. Now I am going to keep a plane in such a manner that, see, I am going to keep a plane passing through center of the top face and center of the bottom face. See what I am going to do? See, I am going to cut the top face and cut the bottom face with an imaginary mirror plane. With an imaginary mirror plane. So it's an imaginary plane. Okay. If I reflect, this half will reflect to other side, and that side will reflect to this side. This is I have kept a imaginary mirror plane, okay, which is passing through two opposite faces. Here it is passing through the top face and the bottom face, right? Two opposite faces. If you do reflection, this half will reflect to that side, and this half will reflect to the opposite side, so you will get equivalent shape. Listen, and this plane, keep this point in mind, this plane passing through the two opposite faces. And in a cube, you know very well there are 6 faces. Okay, so if a plane passes through two opposite faces, then how many planes are possible, okay, in a cube which has 6 faces totally? The answer is that there are 3 planes like this. There are 3 planes passing through opposite faces. Just take down like this, opposite faces. There are 3 planes of symmetry passing through opposite faces. Okay, take down. Now listen, I'll show you another set of planes that is possible here. Okay, another set of planes. So let me draw a cube again. Just draw a cube.
Sir?
Now I'm going to show you another sets of planes. Okay, how they exist in cube. Let me explain that. Listen, you just keep a plane, imaginary plane, passing through opposite edges. Suppose I'll take this edge and the exactly opposite edge. See, this and this are exactly opposite, diagonally opposite edges. Now you just keep a plane passing through that. Okay, I'll keep a plane here. You just keep a plane here. Now this plane, which is passing diagonally through this cube. Now if you do reflection, listen, this downward part will reflect here and the upward part will reflect down. Therefore you will get equivalent shape. Okay, so this is a plane of symmetry. This plane passing through opposite edges of a cube. Yeah, it is called diagonal planes. Yes sir, you're right. So here, listen, each plane passing through opposite edges. Since a cube has 12 edges, okay, we have 6 diagonal planes like this. Okay, so we have 6 planes passing through opposite edges. 6 planes passing through opposite edges. These are the planes of symmetry present in cube. So what is the total number of planes? 3 planes passing through opposite faces plus 6 planes of symmetry passing through opposite edges. So totally 9 planes of symmetry are available. 13 axes, 9 planes. Take note. So now let me show one more symmetry element. Apart from axis and plane, we have one more symmetry element called the center of symmetry or body center. Okay, let me show that. Center of symmetry. Center of symmetry. See, in a cube, just draw a cube. Now, you take the center point. from the center point you draw a line to any point on the cube, or to a corner. For example, I'll draw a line to this corner. Exactly in the opposite side with the same distance, I'll get a similar corner. This is possible in the entire side of the cube. You can draw in this line, this side, that side, this side. Okay, that means if I do inversion about this point, I'll get equivalent shape. So this cubic shape has one center of inversion. Okay, it has one center of inversion. Keep this in mind, right? You know very well, generally a particular object or a molecule or a shape, okay, they have only one center of inversion, right? Shape having two or more inversions are not possible actually. Keep this in mind. Center of symmetry is always only one for a given shape. Now what I'm going to do, so what are the total number of symmetry elements? Take book. Total number of symmetry elements. How many symmetry elements are there totally? Right? There are, let me count. So let me go to the previous page. There are 13 axes plus there are 9 planes plus 1 center of symmetry. Therefore, a cube has 23 symmetry elements in total. Okay, take down. What I am trying to say, how many, by combining these symmetry elements for different shapes, theoretically we can get 32 different groups. Okay, 32 different groups. These are all called crystallographic point groups. Okay, so for each and every crystal must belong to one of this group containing certain number of symmetry elements. So for example, just now we discussed cube. Cube has 23 symmetry elements, right? Like that. So 23 symmetry elements will form one group. Like that, different combinations of symmetry elements in different shapes. If you count the total combinations, we get 32. So in crystals, there are 32 point groups possible based on symmetry elements. Take down. Space, lattice. Space, lattice. Let me go a little faster now. What is a space lattice? See, space lattice is purely a mathematical concept. Okay, it is just an imaginary one. It is imaginary. It's not real. Okay, what is actually space lattice? Listen, you arrange points. Okay, you take some points, arrange them three-dimensionally in a regular manner. Okay, in a definite order. Okay, so what is space lattice? Space lattice is the arrangement of points, some points. Okay, is the arrangement of points, okay, in a definite order. Okay, in third dimension. Take note. Another important. Listen, the neighbors of each point, right, are actually same. Okay, or surrounding, right? Surrounding of each point, okay, is actually same. Right? So you take a point and just observe the surrounding. That means how the neighboring points are there. Okay, and this arrangement exists for all the points, and each and every point has the same arrangement, okay, in the neighborhood, right? Take note. This is what we call the space lattice. Range in a three-dimensional manner like this. See, for example, I'll keep a point here, I'll keep another point here, another point here, then another point here, another point here, another point here. Okay, I'm just arranging points, right? In a perfect order. In a perfect order like this. So I'm just arranging points, right, in a regular manner, okay, for long distance, three-dimensionally. See, I have shown only one layer here. Like that, we have so many layers. Okay, that three-dimensional arrangement of points, okay, is what we call as a space lattice, right? See, we by imagination we are constructing this. Okay, it does not exist in reality. That's why I give not real. Clear? Yeah. Now I'm going to show you a three-dimensional space lattice. Just observe carefully. I'm just showing you a three-dimensional space lattice. Okay. Just observe carefully. This is purely a mathematical concept. Right? I have drawn. Listen, I just shown you a small picture of a space lattice. What I did here, listen, these are all points. I have a point here, I have a point here, I have a point here, I have a point here. Okay, I have points. These are all points. These are all points. Now, what I did is, I have arranged the points in a three-dimensional region like this. And listen, I just stopped to some extent, but actually you have to repeat this in all the directions. You have to repeat. And I just connected adjacent points using straight lines. Okay, so what I did here, I took many infinite number of points, and I arranged them in a definite order. Then I joined the adjacent points using lines, straight lines. If I connect them like this, I will get a picture which looks like a building block. See, the picture looks like a building block, right? So the imaginary points are points, okay, infinite number of points which are arranged in a definite order in three dimension, right? And if you join the adjacent point using straight line, then that arrangement look is what we call as a space lattice. This is called space lattice. Here, listen, we don't know what is those points. What are those points? We don't know. Okay, we took some points and we arranged the points in a particular order, right? And we connected the adjacent point using straight line, and we got some picture which looks like a building block, and we call this building block as space lattice. This is called space lattice. Next one, what is mean by motif? Motif, right? Motif. Take note. Listen, motif can be a atom, motif can be molecule, motif, or some people call it as a basis. Basis, okay, motif or basis. The motif can be an atom or a molecule or group of atoms, collection of atoms, or group of molecules, or it can even be ions. Okay, we call them as motif. If atoms or molecules or group of atoms or group of molecules or ions, okay, if they present in the place of these points, okay, instead of these points, some I told you these are all some points. Okay, now you replace those points. In the place of those points, you just keep atoms, or you just keep molecule, or you keep group of atoms, or you keep group of molecules. You will get a structure which is what we call as crystal lattice. Okay, when you replace this motif by, when you replace these atoms points, when you replace these points, they are all just points. If you replace them by motif or basis, then we get, okay, what is called crystal lattice. Okay, so listen, space lattice plus motif or basis, right? You take the crystal lattice, in the place of those points you place the motif. Motif means it can be atom or a molecule or group of atom or group of molecules or ions. If you place them here, right, then we get what is called crystal or crystal lattice. Crystal lattice. Space lattice is imaginary, but crystal lattice is real. Crystal lattice is real. Why? We have a lot of crystals where the points are occupied by motifs. Okay, so observe carefully hereafter. These points, right, also called lattice points. Lattice points. These lattice points are occupied by motif. Occupied by certain kind of motif. Okay, it depends upon what crystal that you are taking. Okay, take note. Important one is the unit cell. What is a unit cell? Listen, you take a crystal lattice. Listen, you take a crystal lattice. Okay, you just break the crystal lattice into small pieces. Just for understanding purpose, I am saying like this. Okay, you take a crystal lattice and break the crystal lattice. Break the lattice into small pieces. Okay, now you will get a smallest piece. Take a smallest piece. Take a smallest piece, right? Now prepare same number or similar number of many number of that smallest piece. I repeat, take a crystal lattice. Just listen, for understanding purpose I am saying like this. Take a crystal lattice, break the lattice into small pieces. Okay, make it into very small pieces, and take a smallest piece. Prepare many number of the smallest piece. Okay, prepare many number of the identical pieces. Identical smallest piece. Observe carefully. Just for understanding purpose, I am giving this point. Okay, but the definition is not like this. It is somewhat different, but just for understanding purpose. Prepare many number of identical smallest piece. Then join them. If I get, you take the many number of smallest pieces, join them. If I get the crystal lattice again, then that smallest piece is what we call as, okay, unit cell. It's called unit cell. Suppose if I don't get it, I'm just joining the pieces, but if I don't get the crystal lattice, then that is not the unit cell. What you have to do, again you take another smallest piece, okay, and prepare same number of those smallest pieces and again join them. For one particular smallest pieces, okay, you can form the entire crystal. That smallest piece is what we call as unit cell. Okay, take two. This is the way we normally define unit cell. Unit cell, okay, what is unit cell? Unit cell is the smallest portion. Unit cell is the smallest portion of a crystal. Okay, it is the smallest portion of a crystal, which when repeatedly join, okay, join in third dimension can give the original crystal. Okay, that smallest portion is what we call as unit cell. Unit cell is the smallest portion of a crystal, which when repeatedly join in third dimension can give the original crystal. Okay, this is what we call as unit cell. For every crystal, there exists a particular unit cell. Okay, say calcium carbonate, yes, it has a particular unit cell. Right? You take sodium chloride has a particular unit cell. Zinc oxide, yes, it has particular unit cell. Similarly, every crystal has a particular unit cell. Okay, listen carefully. What is meant by a primitive unit cell? See, initially crystallographers thought that, okay, in every crystal only primitive unit cell exists. Okay, initially they started the research in this manner. Okay, what is a primitive unit cell? If the number of motif per unit cell is equal to 1, then that unit cell is called primitive unit cell. Okay, number of motif per unit cell. We can also say in a just understandable manner, okay, we can say like this: if motifs present only at the corners of a unit cell, then the unit cell is called a simple unit cell or primitive unit cell. Okay, take